Imagine a scenario where the most intense solar storm in 20 years has just struck Earth. Fortunately, the damage was limited, but astronomers remain on high alert. The Sun is currently in one of its most volatile solar cycles in decades, and a massive sunspot has formed. This spot is reminiscent of one that caused significant disruptions in the US many years ago. If it continues to grow, the situation could become dire. Depending on how events unfold, the storms could either treat us to vivid auroras or incapacitate our communication and power grids within minutes. On May 11, 2024, Elon Musk expressed his concerns on social media, sharing a sobering graphic that illustrated the stress the last solar storm placed on SpaceX's Starlink satellites. A violent stream of particles from the sun had bombarded the satellites, pushing their protective systems to their limits. Musk warned that a more severe storm could potentially overwhelm or even destroy this technology. The implications would be catastrophic. Not only would terrestrial internet and mobile networks fail, but a swarm of damaged satellites could turn into hazardous space debris. Musk remarked that we've been fortunate so far, but both he and SpaceX are deeply concerned about what's to come. Solar storms are considered one of the most underestimated risks of the century. Experts have long warned about the potential for a once-in-a-century storm that could challenge our entire civilization. Particle streams from the sun interacting with Earth's magnetic field not only create stunning auroras but also pose serious risks to our technology. These geomagnetic storms, caused by streams of charged solar particles, are beautiful yet dangerous. The particles are typically captured by Earth's magnetic field, concentrating over the poles. When trapped, they eventually lose their charge, producing the captivating light shows known as auroras. The strongest solar storm in 2 decades recently created auroras visible much farther south than usual, offering spectacular displays of green, purple, blue, orange, and even red hues. However, the experts caution that these extreme storms are likely to continue for some time. While we may enjoy the breathtaking sights, the potential damage they can cause remains a pressing concern. Solar storms can unleash massive amounts of charged particles within 20 to 30 minutes, leaving minimal time for preparation. This unpredictability makes them particularly dangerous. These storms often stem from sunspots or coronal mass ejections, CMEs. Sunspots are cooler, darker regions on the sun's surface caused by intense magnetic activity. They can disrupt normal convection processes, leading to the release of immense energy and particles in explosive bursts. Currently, attention is focused on a sunspot cluster designated AR3664. This cluster has combined 16 smaller sunspots into a colossal formation visible from Earth with solar-safe glasses. Measuring several times the size of Earth, this sunspot has already triggered powerful solar activity, including 75 medium-class, M-class, flares and 10 of the most intense, X-class, flares in just 1 week. Notably, an X4.5 flare erupted on May 3, 2024, followed by several other significant flares. These ejections not only release vast amounts of energy but can also generate larger CMEs capable of reaching Earth within hours. We are currently in the peak of an 11-year solar cycle, marked by extreme and often unpredictable fluctuations in solar activity. This solar maximum is particularly concerning, as it arrived earlier than expected, suggesting unusual activity within the sun. Scientists are speculating that the sun's magnetic fields may be reversing, potentially leading to more frequent and intense geomagnetic storms. The last major solar storms, known as the Halloween storms of 2003, reached G5 intensity, the highest level, causing global disruptions to power grids and satellite communications. Auroras from these storms were visible as far south as Florida and Mexico. Projections indicate that AR3664 could produce storms of similar magnitude in the coming weeks. At present, AR3664 is not directly facing Earth, providing a temporary reprieve. However, it will soon rotate back into alignment, raising the risk of severe geomagnetic storms. Monitoring this sunspot cluster closely is critical to mitigate potential impacts on Earth and its technological infrastructure. To understand the gravity of the situation, consider the Carrington event of 1859, the most powerful solar storm in recorded history. This event, observed by English astronomer Richard Carrington, began with an exceptionally bright flash of light on the Sun. The resulting coronal mass ejection reached Earth within 17.6 hours, unleashing geomagnetic storms of unprecedented intensity. The effects were extraordinary, with auroras visible as far south as Cuba and Hawaii in the northern hemisphere and as far north as Santiago, Chile, and Queensland, Australia in the southern hemisphere. The Carrington event caused significant disruption to the telegraph systems of the time, which represented the pinnacle of communication technology. Equipment failures, sparks from telegraph wires, and fires were common, highlighting the vulnerability of human infrastructure to solar storms. If a storm of similar magnitude were to occur today, the consequences for our technology-dependent society could be devastating. The stakes are high as we navigate the risks posed by solar storms. While they offer awe-inspiring displays, their potential to disrupt modern life is a sobering reminder of the power of our Carrington event, star. A massive solar storm, had a dramatic impact on the technology of the time, though it was relatively minor compared to the risks our modern, tech-dependent civilization would face if such an event occurred today. While some devices were destroyed by the storm's electrical surges, others operated using the energy generated by the solar activity. If a similar storm struck now, it could severely disrupt satellites, power grids, GPS, and communication systems, with potential economic damages in the trillions. Critical systems like air traffic control and navigation could fail, leading to major accidents and disasters. Solar storms are caused by intense magnetic activity on the Sun, which produces solar flares and coronal mass ejections, CMEs. Flares are sudden bursts of energy resulting from the release of magnetic energy in the Sun's atmosphere. These events emit high-energy particles and light across the electromagnetic spectrum, traveling through space at incredible speeds. CMEs, on the other hand, eject massive clouds of magnetized plasma that can take hours or days to reach Earth. In 1859, the CME's energy was so immense that the plasma cloud arrived in less than 20 minutes. A truly extraordinary event. Solar storms have both positive and negative effects. Streams of particles from the Sun, including protons, electrons, and heavier elements, are essential for maintaining the heliosphere, a protective bubble that shields our solar system from interstellar cosmic rays. Without these streams, life on Earth might not exist due to exposure to extreme cosmic radiation. However, these same particle streams can also pose serious threats to our technology. The Earth has likely experienced countless such storms over its history, but our modern reliance on electronic systems makes us far more vulnerable. Efforts to protect against solar storms are ongoing. Modern satellites are designed to withstand space weather, but many older satellites and electrical systems remain at risk. Governments and power companies are developing new technologies to safeguard power grids, substations, and plants. For instance, the geomagnetic storm of 1989 caused a massive blackout in Canada, highlighting the need for better infrastructure resilience. Satellite systems, including the International Space Station (ISS), are particularly vulnerable to high-energy particles, which can damage electronic components and disrupt operations. Space agencies like NASA and NOAA actively monitor solar activity using satellites such as the Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory, SDO. These observatories provide real-time data on solar flares and CMEs, helping researchers study the Sun's structure, magnetic fields, and ejections. This data allows for space weather forecasting, giving satellite operators, power grid managers, and aviation authorities a chance to take preventive measures. However, predicting the precise timing and intensity of solar storms remains challenging, as flares and CMEs can occur suddenly, sometimes with only minutes or hours of warning. Improving our ability to predict and mitigate the impacts of solar storms requires continued investment in space-based observatories, advanced computational models, and international collaboration. Solar storms can disrupt GPS systems, which depend on accurate timing signals from satellites, causing errors that could affect aviation, telecommunications, and other industries. Preparing for extreme space weather events involves strengthening critical infrastructure, developing emergency response plans, and investing in technologies that can withstand electromagnetic interference. Public awareness is also essential. Educating people about the risks of solar storms and how to prepare for potential disruptions, such as having emergency supplies and backup power sources, can reduce the impact of prolonged power outages caused by geomagnetic storms. Ongoing research into early detection and space weather modeling will enhance our ability to predict solar storms and develop more resilient technological solutions, ensuring a safer and more prepared future for our interconnected world.